Welcome to The Explainer. Look, let's just jump right into it, because there is a monumental shift happening in computational biology right now. We're rapidly moving away from just using AI to predict the shapes of proteins, and we're entering this wild new era where AI is actively designing medical interventions. But, as you can probably guess, with that massive leap in power comes a huge risk of losing our scientific rigor. So today, we're unpacking how a framework called EP, the energetic paradigm, steps in to turn AI drug design from a chaotic model race into a truly reproducible, scientifically controlled system.
Here's a quick roadmap for us today. We'll start by moving beyond structure prediction, then we'll tackle the closed AI problem, introduce the energetic paradigm, build out the evidence graph, break down the 6-layer architecture, and finally, look at how we redefine scientific trust.
All right, Section 1, Beyond Structure Prediction. To really wrap our heads around this transition, think about a classic lock and key metaphor. For a while now, amazing open source tools like AlphaFold 3 have been showing us exactly what the biological lock looks like. That's structure prediction, right? It answers the what. It's descriptive. But newer systems, things like ISO-DEE, they've got to answer way harder, prescriptive questions. They need to tell us which key fits, if it opens the right door, and whether it's actually going to survive inside a complex living cell. We're literally moving from snapping a picture of a lock to actively manufacturing the perfect key.
And this perfectly illustrates how AI drug discovery is totally leaving that clean, predictable benchmark world. We're talking about systems reasoning through binding affinity, recognizing antibody targets, inferring function from sequence, and, get this, directly telling the wet lab what to experiment on next. The source even highlights how an AI like ISO-DEE pinpointed a hidden cereblon binding site that literally took laboratory scientists years to find. But here's why you should care. In this prescriptive world of intervention design, a wrong prediction isn't just a dropped point on some leaderboard. No, a bad guess can waste months of incredibly expensive wet lab work and send entire drug pipelines down a dead end. Which brings us right to Section 2, the closed AI problem. Because as these models get more powerful, they're increasingly being locked behind corporate walls. So we have to ask ourselves a pretty tough question here. With private data and undisclosed architectures becoming the absolute norm, can we really trust closed scientific AI, especially when we can't even independently examine how it fails or how it was trained? Well, here is the absolutely crucial takeaway. A high benchmark score is not yet a scientific claim. It just isn't. It's an outcome. As outside researchers, we might see a really shiny, impressive result, but we can't tell the difference between actual algorithmic progress, a massive private data advantage, or just narrow overfitting. So the crisis here isn't just some philosophical open source versus closed source debate. It's a fundamental loss of scientific controllability. Think about it. Private data completely obscures what the model can actually do. Hidden mechanisms mean we can't check its assumptions, and benchmarks, they frequently miss real biological failure modes entirely. An AI might spit out a binding pattern that looks flawless on a computer screen, but it completely fails in a living cell. Right now, commercial incentives are just rewarding secrecy way more than they're rewarding reproducible science. Okay, Section 3, Enter the energetic paradigm. This is how we actually fix the control problem. This is the exact turning point where EP, the energetic paradigm, steps into the picture. It provides that much-needed research control architecture we need to actually judge systems like ISO-DEE responsibly. Now, what's really fascinating here is that EP isn't just about controlling AI. It entirely reframes the whole process. Intelligence isn't just a black box model spitting out an answer anymore. EP is the architecture that rigidly connects the biological question to uncertainty, to model prediction, to a molecule candidate, to assay feedback, to failure memory, to the claim boundary, and finally, to reproducible science. It's an end-to-end energy flow system. Let's see how this works in practice in Section 4, Building the Evidence Graph. Say an AI discovers a hidden binding site. Under the EP framework, that discovery isn't treated as some miraculous, unexplainable event. It has to be mapped out as an energy path. You have to validate why that site exists, under what specific state, and for what exact class of ligand. It takes a wild prediction and forces it to become a controlled, testable hypothesis. Also, EP gives us a huge warning. Relying on raw binding affinity alone is incredibly dangerous. A molecule might bind super tightly in a simulation, sure, but if it's highly toxic or insoluble or totally misses the target in a real human body, it's completely useless. That's why EP forces that affinity score inside a strict causal evidence chain. It guarantees the system doesn't just optimize some attractive metric while completely forgetting the actual biological purpose of the drug.
And I absolutely love this next concept. Under EP, failure is totally reclaimed. Failed molecules, dead-end pockets, busted assays, they aren't just tossed in the trash. They are preserved as vital boundary information. By storing all this negative knowledge, the system actually learns where not to go, which makes every future search so much more efficient. So how do we actually build this? Section 5, the 6-layer architecture.
This is a really clean, practical stack designed for top-tier science. Layer 1 defines the biological objective, the disease mechanism itself. Layer 2 handles the structural mapping. Layer 3 tracks the constraints and risks, like toxicity. Layer 4 brings in the wet lab experimental feedback. Layer 5 stores those failure states we just talked about. And Layer 6 strictly governs the final claim. It literally prevents a basic computational result from being overhyped as a medical breakthrough. It's the whole shebang, a complete protocol.
And finally, Section 6, redefining scientific trust. Let's look at how this changes the game for future breakthroughs.
We learn that the ultimate standard we need to strive for isn't actually ideological openness. It's scientific auditability. This is a massive paradigm shift, right? Because it means a proprietary, closed-source model is actually fine, as long as it provides an evidence graph, strict data provenance control, and clearly defined boundaries for its claims. You don't have to leak your proprietary code, but you do have to prove exactly what evidence is powering your result.
So what's the big takeaway from all this? EP defines exactly what makes a claim controllable, testable, and trustworthy. By changing the core unit of intelligence from just the AI model to the fully controlled research system, EP ensures we aren't just running a blind race for better benchmarks. We are laying the auditable foundation for the entire future of medicine. Which leaves us with a pretty provocative question. Now that we finally have a blueprint for reproducible AI science, how quickly is the pharmaceutical industry actually going to adopt this much higher standard of proof?